All right, 10.6 is our last section inside of Chapter 10 that we're going to be taking a look at. And what we're going to be doing is we're going to be combining what we did in the last section in 10.5, polar equations, with what we did in the first section about conics. And we're going to start with Theorem 1016. Theorem 1016 is a classification of conics theorem. And we're classifying our conics by their eccentricity. All right, so we're going to let F be a fixed point. That fixed point is the focus. And D be a fixed line. Called the directrix. Both of those are familiar words to us in the plane. And then we're going to let P be another point in the plane. And let E, which is the eccentricity, be the ratio of the distance between P and F to the distance between P and D. So we've got distances. One of the ways you can write distances is by the points that they're defined to be, without any symbols around them at all. So the eccentricity would be the ratio of the distance from P to F, like this, divided by the ratio of the distances from P to D. So we're finding the distance between PF divided by the distance between P to D. And we're just measuring a point that's on our plane curve back to the focus or back to the directrix for each of those. All right, so the collection of all points with the given eccentricity is a conic. And the conic that it is depends on the value of E. So if E is between 0 and 1, we have an ellipse. If the eccentricity is equal to 1, we have a parabola. And our third option is if the eccentricity is greater than 1, then we have a hyperbola. So we're going to take a look now at the polar equations of our conics. And I do want to warn you that I'm going to present this slightly differently than your book presents Theorem 1017. This was actually in a book that I had used a while back, and I like it a little bit better, and I think it helps to clarify what's going on a little bit better, so we're going to use it. What Theorem 1017 in your book actually does is it compacts all the formulas I'm going to give you into one formula, which has its benefits, but for the purposes of what we're doing with them, I think it might be more helpful to see them separated out. So these are the polar equations of conics. So we have the conic with eccentricity E is greater than 0, with a focus at 0, 0, and the indicated directrix. And it will have, or it has, the polar equation that follows. All right, so we have 4 options. So option number 1 is that the equation is R equals the eccentricity times the directrix divided by E cosine of theta minus 1. This occurs for directrix x equals d, where d is positive. Okay? The second one is really similar. The equation is the same thing, except it has a positive sign underneath. So it's ed over e cosine of theta plus 1. I totally have those backwards. I apologize. The first one should say plus 1. I got off of my lines. The second one's supposed to be minus 1. Let's get that fixed. Minus 1. Okay? And this is for directrix x equals d, and d is negative. Okay, so positive 1 gives you a positive d value, and negative 1 is a negative d value, if you want to look at it and think about it that way. So these are both with directrix that are vertical lines, right? X equals d is the vertical line. There are options, too, for our directrix to be a horizontal line. So this is the next two. R equals the ed. What changes is the equation's trig value that's being used. So it's e sine of theta plus 1. And much like the other one, we're going to look at the directrix and whether it's positive or negative. So this is y equals d, and d is positive. Again, a positive value gives you the plus 1. So what happens on 4 is I have r equals ed over e sine theta minus 1, and this works for directrix y equals d still, but d is negative. Okay, so we're not going to do a whole lot with this in this section. This is a very brief section, but I'd like to kind of point out where these are all coming from, these formulas, as a note. And you can go for further explanation if you'd like into your book. Each of these formulas is derived from the square root of x squared plus y squared equaling e times d minus x, along with a change of variables into polar coordinates. Okay, so that's where these formulas are coming from. I'm not going to ask you to derive them or anything like that, but that is where they're coming from. So we're going to do, with 3 examples in this section we're going to do. So first example, we're going to find the eccentricity. And distance from the pole. That's the D value above. To the directrix, right? That's the distance to the directrix, excuse me, of the conic. And we're actually going to sketch too. Then we're going to identify and sketch the graph. Identify means we're going to decide, is it a hyperbola, is it an ellipse, is it a parabola? All right, and the example we're going to do has the following equation. R equals 6 over 2 plus cosine theta. So this kind of feels a little bit like when we were working with the geometric sequences and series, specifically series back in chapter 9. And we were trying to make it look like the form a over 1 minus r. Specifically, we wanted the 1 minus at the beginning. Well, this is much the same thing. I want to try and make it look like one of these equations, right? And because I've got cosine in my denominator and because I have addition in my denominator, it's the first equation that it's going to try and mimic. Notice I do have it to being a plus 1. It's written at the end. My plus 2 or positive 2 is written at the beginning. So I can shift that to the end, but I don't want it to be 2. I want it to be 1. So what we're going to do as we rewrite this is we're going to divide the entire, I'll write it here actually, the entire equation by 2 on the top and on the bottom. So if I do that, I get 6 on top. And then on bottom I have the the cosine of theta becoming a 1/2 cosine of theta. I'm just going to put it into the same pattern, the ordering of the formula above. And then it would be plus 1. So with that in mind, we should be able to identify the E and the D that we're asked to identify in the directions. So in this one, E would be at the beginning right in front of cosine. So E is actually equal to 1/2. And the fact that E is equal to 1/2 also tells us what kind of a conic we have. So since the 1/2 is smaller than 1, namely it's between 0 and 1, we have an ellipse. So this picture is going to be an ellipse. So we've identified that. We can also find D. So D is on the numerator, right? So in the numerator I have an E and a D. I know E is 1/2, so in order to have the numerator be 3, the D would have to be 6. So my D is 6. And D equals 6 is telling me that my directrix is x equals 6. And again, why is it x equals 6? Well, because we're in number 1, right? The case number 1 up here, and it's an x equals that D value. All right, so we're going to change to the grid. I think that one's probably our best. Maybe the medium. Medium's pretty good. Okay, so we're going to do our medium grid. And we're going to sketch what we have. So I have, so just forgive me that I'm not the best artist in the world here. I got them lined up pretty well at this point. Directrix, we can draw that in. That's no problem. So we will draw in a directrix at x equals 6. I think it's right here, except I'm a little bit too far to the right. All right, I think I got it. So that's the line x equals 6. That's my directrix. All right, so from here, we're actually going to just use our calculator to finish filling in our graph. So if you grab your calculator, and we've talked about polar coordinates before, but in case you're watching this and you haven't got your calculator set up to do so, make sure that your mode is in polar mode. So you can hit mode, and make sure that it's got about 3 or 4 lines down. It says function, parametric, polar. You want it to be in polar. And then in y equals, we're going to put in the equation 6 over 2 plus cosine theta. Or if you wish, you could put in, oh, I did actually have a typo up there. I'm seeing it now that I'm looking back at my equations. There's a 3 that's supposed to be up here. I'm so sorry. The 6 was supposed to be divided by 2 to give me a 3. My bad. Okay, let's try again then. So you can either put in 6 over 2 plus cosine theta, or you could put in 3/1/2 cosine theta plus 1. Either of those is perfectly fine. Your window can go from 0 to 2 pi for your theta value, right? And if you want to do like a negative 10 to 10 window, that would be sufficient. If you want to do it a little bit smaller, that would be okay as well. Mine's actually set up as negative 7 to 7, which is enough. And if you take a look at the ordered, or well, the x coordinates where it crosses, it's crossing at 2 over here, and it's crossing at 6 on the left, right here. Okay, and if we connect these, roughly speaking, with an ellipse, which we identified that it should be, we would have, okay, I'll have to shift it over as soon as I get mine drawn, because I didn't draw very well. It is a height of almost 4. It's pretty decent. Okay, I'm going to shift it over. So my graph, an ellipse, looks something like that. I could easily find the center at this point, right? So the distance all the way across goes from -2 to -6. If I've drawn, I'm sorry, +2 to -6. That's 8 across. So my distance should be halfway in between. Should be here at did I get 6? 1, 2, 3, 4, 5, 6. I did. Should be here at 2. So 2 from the, now on the negative side, -2 would be my center of my ellipse. Okay, so the next ones we're actually going to go in reverse order, not with the graph per se, but with the information. Instead of being given an equation and identifying information, we're going to be given information and we're going to create an equation. So on numbers 2 and 3, the directions will be the same, and they say the following. Find the polar equation for the conic. And it gives us some information. So on number 2, it tells us that the directrix is x equal to 2, and that the eccentricity is 1.2. Now, because the eccentricity is bigger than 1, this tells us necessarily that it's a hyperbola. We aren't exactly told that we have to write that down, but it would be a good thing for us to sort of be aware of. We have a hyperbola here. And our equation that we're going to create is r equals, so it should be ED over E cosine of theta. Now my D value is an x equals equation, and it's positive. So if you look at the options over here, x equals means you're in case either 1 or 2. And then the fact that x, the D, is positive means we're in case 1. So it's E cosine theta plus 1 as our denominator. All right, so E is the 1.2, and the D right here is the 2 that's being given. So we have the following equation. R equals, we have 1.2 times the D value of 2 over the E, which is 1.2 again, cosine theta plus 1. Okay, really all we can do in terms of simplifying is just to clean up the top to write it as 2.4, right? So 2.4 will be divided by 1.2 cosine theta plus 1, and this would be the equation of this ellipse, excuse me, this hyperbola that I identified. So this one was in case 1. All right, the second one, problem number 3 specifically, gives us the same kind of information. This one tells us that the directrix is x equal -2. The eccentricity is equal to 1. So since the eccentricity is equal to 1, that tells us that we have a parabola, right? And our equation, r equals, fits one of our cases. Namely, I still have an x equals, so it's in case 1 or case 2, but now my directrix, x equals -2, is negative, so d is negative, so we're in case 2 for this one. So this is case 2. And we're supposed to be writing down the same thing we had above on the previous one, but instead it's divided by the cosine of theta, and it's got a subtraction sign with 1. Now the eccentricity is 1, and the directrix is -2, so I have 1 times -2. And the eccentricity goes on bottom. The eccentricity being 1 goes on bottom. So this equation ends up being r equals -2 over cosine of theta minus 1. And that's all we're going to really be taking a look at in this section. The homework is page 743. It's not very long. Be prepared. 15, 16, 17, 33, 36, and 38.